Hello scientists, this is Miss R and we're going to talk about Lab 5.10. We're going to be using this simulation, the energy forms and changes in Phet, as well as one of the K-12 simulations. We're going to start in the Phet simulation that's going to look something like this. We're going to try to boil water and freeze water and watch what happens to these little energy symbols. This is up in the right-hand corner of the simulation. I'll show you in a moment. Make sure that this is checked so you can watch those energy symbols. You're also going to want to be on the intro part for the first half of this lab. When you click on the Phet link, you're going to come up to this screen and hit play or download. And it should start to run. If it doesn't, you may have to update your Java. Mac users, you're going to have to go to your downloads and right-click or control-click on the program so it will run. Trust me, it's a very safe program. I've had absolutely no problem with students downloading viruses. This is a very reliable site. This is what the simulation looks like. We're on the intro tab here in the upper left-hand corner. I know you can't see it because it's just outside of the box. What we do want to click here is energy symbols. You're going to see different little squares here that represent amounts of energy or units of energy. What we're going to do first here is try to boil some water, and we're going to put it on top of one of these little racks here and turn up the heat. And you can see that the energy symbols are going from the heat source into the water. And you know that temperature is the average kinetic energy of the water. So you can see that the energy of the water is starting to increase, and some of that energy is starting to leave the water as some of the water starts to leave the container. If you've ever boiled water in a tea kettle, or maybe you were making some boiling water for your mac and cheese, you know that once you get water really boiling, some of the water starts to leave the container. In fact, a lot of the water, if you put your, I don't recommend putting your hand there, but if you put some sort of other pan or maybe a wooden spoon or something, you'll see that it's going to get wet. So we know that our water is boiling because a considerable amount of the water is leaving, and some energy is also leaving with that water. Some energy can leave if the water is not boiling, but we know this water is boiling because there's a considerable amount of steam. So now we get to chill the water. Let's see what happens when we chill the water. Let's hit play here. Add some ice, and we can see that the energy is leaving the water. It's going from the water into the ice. Just if I pick up this cold slinky, or it feels cold at least, the energy from my hand is going into the slinky to warm it up. The cold isn't leaving the slinky and going into my hand. Cold doesn't travel, but heat is leaving my hand to warm up the slinky, and that makes my hand feel cold. No more energy is leaving the water, and I don't see the thermometer. Well, it's still more energy is, well, it's like kind of an equilibrium. I think perhaps if the recording showed that the water was a solid, it would be frozen. So back to the lab sheet. We've done number 1. Is it possible to freeze the water and boil the water? We've talked about that, about energy coming and going, and the water being at equilibrium. It's staying at the same temperature. Water that's boiling will stay at the same temperature, so you could put a thermometer in there too and check that that water is staying at the same temperature. And frozen water will also stay at the same temperature. Ice is always, well, it can get a little bit colder, but it generally doesn't while it's freezing. Ice will be 0 degrees Celsius the entire time it's freezing, and then it will start to get colder if the temperature is any colder. So watching that thermometer, if it levels out for a while, that's a good indicator as well that the water is boiling If it's a high temperature for a while, that stays the same, and or if it's frozen, it will stay at the same temperature for a while until all the water is frozen. We've already chilled the water, so we're going to go back and add heat and observe and notice at least 3 things about energy. We'll keep that energy symbols box checked. Then we're going to heat some iron and brick at the same time. We're going to figure out which one can hold more energy and how they lose their energy. So we're going to go heat some cold water, and we're going to heat iron and brick and see what happens. So we have some nice cold water here. It looks like the temperature is pretty stable. So now let's heat it up and see what happens. Move this thermometer over a little bit, add some heat. Now, which direction is the energy going? Is it heading from the flame, from the heat, into the water? So the heat energy is traveling from the heat source up into the water in this case. And then it's traveling out into the atmosphere. Watch the thermometer. It's going to a constant temperature, and it's staying at that constant temperature while the water boils. That water will stay at 100 degrees Celsius or 200 degrees Fahrenheit for under normal conditions, under normal pressure temperature, until all of the water boils off. If you want water to be more than boiling temperature, more than 212 degrees Fahrenheit or more than 100 degrees Celsius, you have to put it under different temperature or under different pressure conditions. Or you just turn it into steam. If we cool water, notice that the heat energy leaves the water. If we heat water, energy goes from the heat source to the water to the environment. If we put it in reverse, that heat energy goes from the environment to the water, well, once the water is cooler than the environment, and then into the colder environment. So the cold doesn't travel into the hot water. The heat energy travels into the ice. All right, now let's put our thermometer back. Now that we're done with water, let's heat some brick and some iron. So watch what happens to the energy symbols. How many energy symbols are going to accumulate in that brick? Watch that versus watch the iron here. You might want to just pause this recording and count how many energy symbols are in this chunk of iron versus in this chunk of brick before the brick starts to let some energy symbols go. What we're exploring here is called specific heat. It's how much heat energy a particular material like brick or iron or copper or bronze or wood can hold, and how quickly they let go of that energy or take in that energy. So we've just looked at number 2 and number 3. We've kind of answered the question, which one, brick or iron, can hold much energy, and how do they lose their energy? It goes to the environment. Did you notice which one loses energy more quickly? Now we're going to add a heated up bit of iron to room temperature water, and we're to describe in detail what happens. Pay attention to those E symbols. So we're going to heat up our iron a little bit. You can see the energy is going from the heat source into the iron. And then we're going to take our nice hot chunk of iron and stick it in room temperature water. So what happens to the energy, the heat energy that's contained in the iron? Does some of it leave the iron, and where does it go? I'll let you think about that. Now we get to do two things at once. We get to place a brick on top of the iron and add heat and describe what's happening in at least 3 sentences, and then keep the brick on top of the iron and cool it down and see what's happening and describe that in at least 3 sentences. So let's add some heat. Let's pay attention what's happening to the energy symbols. Oops, better hit play there. Oh, for some reason it flipped. I want the brick on top of the iron. There we go. Hit play. Oh, it doesn't want to. Here we go. There we go. Okay, let's see what's happening to those energy symbols. So lots of energy is traveling from the heat source into the iron, and then where does it go? Does it go into the brick? Does it go out into the atmosphere? All right, let's see if we can cool this system down. So where's the energy going here? Some of what's happening to the energy in the brick and what's happening to the energy in the iron. Is it leaving the brick iron system and heading into the ice? I think that's about as cold as it's going to get. No more energy seems to be leaving. Seem to be pretty much at equilibrium here. So write down what you noticed when we cooled and we heated the system. Let's look what happens to this brick when we start to heat the iron again. The iron gets hot, some energy goes into the iron, and then some energy will leave the iron and head to the brick. So once the brick and the iron are cooled down, do they have the same thermal energy? Why or why not? Did you see the same amounts of E symbols in both the brick and the iron? We're going to talk about specific heat capacity a little bit later in the lab, but feel free to go and look at it on the internet if you'd like and get some ideas about that. If you want to explain brick versus iron in terms of specific heat capacity, you can. Otherwise, you can just write down your observations as well. So let's talk about the Energy Systems tab here. We're going to click the second tab on the top left of the simulation that looks like this. And we're going to set up different systems of energy. We're going to pay attention to the forms of energy box over on the right-hand side of the model. You can see that if the E symbols are gray, it's mechanical energy. If they're blue, they're electrical energy. If they're red, it's thermal energy or heat energy. The yellow E's are light energy, like you might see in this light bulb here, and the green ones are chemical energy. So for example, in this picture that's in the lab, we have thermal energy here in the tea kettle. The steam is pushing on this wheel, so that's mechanical energy. The generator here is producing electrical energy. It's converting that mechanical energy. Here you can see it's converting into electrical energy. And that electrical energy is being turned into light energy, see the yellow E symbol, and a little bit of thermal energy, because if you've ever put your hand on a light bulb, you know it's a little bit hot. Here's a light here on my desk, and if I put my hand here, it's nice and warm. And that's unfortunately an inefficiency in light bulbs we'll talk about. Your job here is to fill in these green boxes to talk about what kind of energy is being converted to what other kind of energy. Remember, energy can never be created or destroyed, it's just transformed one form of energy to a different form. So we can click the Energy Systems tab and we get this whole different setup here. Let's put the tea kettle in place here. And let's swap out our water for a light bulb. So this matches the picture that we've got. Let's click the energy symbols box here so we can see the different forms of energy that are being transformed here. Let's heat the water a bit, get some steam going from our tea kettle, have that steam that turn into mechanical and thermal energy that runs the generator. The generator is going to transform that thermal and mechanical energy, that thermal energy into mechanical energy, into electrical energy. You can see the electrical energy is going through the wire into the light bulb, and the light bulb is emitting yellow E's, which is light energy, and it's also emitting a little bit of thermal energy because there's a little bit of inefficiency in lights. They don't convert all of the electricity to light, some of it's converted to heat. So now you know how to fill in these green boxes because we've done the setup here. And you will can also fill in the green boxes as we look at the bicyclist and the sun shining on photovoltaic panels. So I'll go into the simulation and set up the bicyclist with the light bulb and the photovoltaic panels, just like I have on my roof, powering an electric burner that's boiling some water. Now we've got an opportunity to look at a different energy system and how things are going to work. You can see that there is some chemical energy in the bicyclist, just like there's chemical energy in you right now. If you ate some food for breakfast or lunch or dinner, you've got some chemical potential energy in your body that can be converted into mechanical energy if you walk around or ride your bike. She needs a granola bar or some gummy bears or something. She was converting her mechanical energy into the generator into electrical energy, and then of course her electrical energy was becoming light energy and thermal energy in the light bulb. Let's set up a different system here. Let's have the sun as our form of energy. Let's use photovoltaic panels or solar cells to capture that source of energy, and let's swap out our light bulb for an electric burner and see what happens. So we have light energy from the sun. It's captured by photovoltaic panels or solar cells that convert it to electrical energy, which is going on in my roof right now because it's a beautiful sunny day out. And that electrical energy is being converted to thermal energy. You can see the red E's right down here in an electrical burner. And that thermal energy is being transferred to the water, and the water's boiling. You can tell the water's boiling here again because the temperature is remaining constant. So there's another set of energy conversions. Just for a little fun here, we can see some real energy conversion going on. This is the output from a computer monitoring system on my solar cells. You can see that those solar cells on my roof are right now making about 3 kilowatts of energy. The green stuff here is the energy we're making, and the red stuff is the energy we're using. You can see that about 6 a.m. when we went down to take a shower and turned on the bathroom fan, that uses a whole lot of electricity, and the water heater does as well. And these spikes here are the water heater continually firing about every 3 to 6 hours to just keep that water hot. And I think I turned on the microwave to make some tea right here. So this is interesting in terms of electrical energy in your own house. If you have one of these monitoring systems, you can see how much you use, and if you have photovoltaic cells on your roof or somewhere else on your house, you can see how much energy, solar energy, you convert to electrical energy. You can see it's been a little bit cloudy in the last 30 days. We've not quite kept up with the energy generated to the energy used, so we had to buy a little bit of energy. but if it keeps being sunny like it has been today, we should catch up. So now it's up to you to fill in these green boxes for what happened when the chemical energy in the bicyclist was converted to other forms of energy. We just talked about solar energy. That's when light energy is converted to something else, and that something else is converted to even a different form of energy. There's one more situation we're going to look at. It's flowing water, and we're going to look at what happens when you put flowing water on a generator like you would at a dam, a hydroelectric dam, and see what happens. So here we've swapped out the sun for some flowing water. We'll turn on the tap here, just like you'd let water from a reservoir flow over a dam into a hydroelectric generator or a hydroelectric plant where there is a generator that converts this mechanical energy from flowing water into electrical energy, and that electrical energy can light your house. And you notice there's a different kind of light bulb here. This is a traditional light bulb, an incandescent, which creates light from putting electricity through a filament and heating it up, which also creates light. A CFL is a slightly different system where you heat up a gas and then it glows. And CFLs are a bit more efficient. So a lot of people are switching out their incandescent light bulbs for CFLs, or now they're switching out their incandescent light bulbs for LEDs, which are even more efficient. They create less heat and more light. So now you know how to fill in these green boxes that we've seen this system at work. And you can compare the two different types of light bulbs. How are compact fluorescent lamps different than the incandescent bulbs? Which one releases more thermal energy, and how is the process different? And if you want, you're welcome to go look up this question online. Just make sure you put things in your own words and cite your source. In number 10, we talked about how this dotted E here represents something. It represents energy conversion. You're welcome to go look up how a generator works online, or you can make some inferences based on what we've talked about for number 10. Part 3 on heat transfer is down here, and that is described in part 2 of the YouTube video. So I'll let you watch the other YouTube video. Thanks everybody for tuning in for part 1 of the video that went over part 1 and 2 of the lab. Good luck!